Hello viewers, welcome to this next lecture on the NPTEL MOOC course on Mathematical Portfolio Theory. You would recall that in the previous two lectures we were talking about risk management and we essentially looked at what is going to be the definition of upper and lower quantiles, and then we moved on to the definition of value at risk and we looked at some of the properties of value at risk. So, in this concluding lecture on this part of the course, we will talk about a couple of deficits that is observed in case of value at risk, and then we will introduce the notion of coherent measure of risk with an emphasis on a particular coherent measure of risk, namely A bar. So, accordingly we start this lecture today. With a brief introduction to coherent measure of risk. So, this is motivated by a couple of observations on drawbacks of value at risk. The first one is that the value at risk or VAR, this provides no information on the sizes of losses in scenarios with probability less than alpha, and secondly, the VAR recorded for a diversified portfolio, and you had seen an example of this, may exceed that recorded for a position with all funds being held in one security. So, we will just have a brief look at the coherent measure of risk at a later stage, but what I want to start off with is a particular case of coherent measure of risk, and that is what is known as the average value at risk or AVAR. So, naturally we are going to start off with the definition of AVAR, and I said that VAR provides no information on the sizes of losses in scenarios with probability less than alpha. So, what AVAR does is actually it takes into account the losses which have a probability of less than alpha. So, then accordingly the AVAR of x, where x is some random variable, is given by the following. So, AVAR alpha of x will be given by all the value at risk at different levels of x with the probability at which the VAR is being calculated ranging from 0 to alpha into d beta, and I take this divided by a factor of alpha. So, this means that earlier what you were doing, you were only looking at VAR alpha of x, and what you are now doing is that, so earlier what you did was you looked at VAR alpha of x by identifying this alpha, and now what you do is that you look at all the VARs that lie here from 0 to alpha with probability 0 to alpha and average them out. So, it is going to be all those VAR at different levels of alpha. So, this I will denote by beta as a variable across which the value ranges from 0 to alpha. So, what I do is that I take all the VAR with probabilities lying between 0 and alpha and I average it out, and that is what is going to give me the definition of the average value at risk. So, what it does is when you are looking at VAR, it was only looking at losses at this point, but average value at risk is now going to look at losses across this entire region so that you do not miss out on any unusual level of loss that might happen in a region with probability being less than alpha. Now, from the definition of var, this can be rewritten as minus 1 over alpha integral 0 to alpha q beta of x into d beta, and this can be rewritten as integral 0 to alpha q of subscript 1 minus beta, that is I switch from upper to lower quantile, minus of x d beta, and I have made use of the result that q alpha of minus x is going to be nothing but q of subscript 1 minus alpha, that is the lower quantile of x. So, here I just want to make an observation, and the observation is the following, that unlike value at risk, that is var alpha, the average value at risk a var alpha takes into account the impact of all losses that occur with probability at most alpha, and also it provides an estimate of losses implied by events in the alpha tail of the distribution of x. So, in an informal sense, I can make the following statement as a consequence, that your a var alpha provides the expected loss, and this comes from the fact that you are doing the integration. So, this is the expected loss conditioned on the worst 100 into alpha percent of outcomes, and this is in contrast to var alpha, which provides the maximum loss in the best 100 into 1 minus alpha percent of outcomes. So, for example, if we choose, so suppose that we choose alpha equal to 0.05. So, in this case, what does var provide? It basically it provides the maximum loss in the best 100 into 1 minus alpha percent scenario. So, that means in this case your var will be the maximum loss amongst 95% of best outcomes. And in contrast, what is going to come out from a var of alpha is that it provides the expected loss on the left hand side of alpha, and so this is going to be the expected loss conditioned on worst 5% of outcomes. So, this is a statement which distinguishes the definition of var of alpha and a var of alpha for the identical alpha. So, now since beta is less than or equal to alpha, remember that your beta ranges from 0 to alpha. So, naturally your beta is going to be less than or equal to alpha, and this implies that from an earlier result of quantiles, this implies that the upper quantile of q of x vis-a-vis the beta, this is going to be less than or equal to q alpha of x. And since this holds, so therefore, it is clear that a var dominates var, And let us see how this statement holds. You can observe that this statement A bar dominates var holds, because A bar alpha of x by definition is minus 1 over alpha integral 0 to alpha q beta of x d beta. So, what I am doing is that I am just making use of this form that I have here. And now that since beta is less than or equal to alpha results in the following relation, so that means minus q beta of x is going to be greater than or equal to minus q alpha of x. So, this is going to be greater than or equal to minus 1 over alpha integral 0 to alpha into q alpha of x into d beta. Okay, now if you observe carefully, q alpha of x is a constant quantity. This is going to be minus 1 over alpha q alpha of x, and integral of d beta from 0 to alpha is alpha, which cancel out. So, this ends up being equal to minus q alpha of x, which by definition is var alpha of x. So, this shows that, so therefore, a var alpha of x is going to be greater than or equal to var alpha of x. So, that means the estimation or the risk measure value of the risk measure as given by a var is going to be at least under no circumstance be less than the value given by the var. So, that means that a var gives you a more conservative estimate as far as your risk perspective is concerned. Okay, so we just state a few results as we had done in case of value at risk. So, for x less than or equal to y and any real number m, we have the following properties. First of all, we have a var alpha x is going to be greater than or equal to a var alpha y. Secondly, we will have a var alpha of x plus m is going to be a var alpha of x minus m. Thirdly, we will get that for lambda greater than or equal to 0, we have a var alpha of lambda x is lambda a var alpha of x. And finally, fourth one is subadditivity. So, then for any x y, a var alpha of x plus y is going to be less than or equal to a var alpha of x plus a var alpha of y. At this point, I am going to just note a lemma, and the lemma says the following, that let x be a random variable and assume that u is a random variable which follows the uniform distribution on 0 1. Then if I define a random variable y as y of x equal to q raised to u x x, then this random variable has the same distribution as x. All right. Let us now state a proposition to give a more concrete form to what is going to be, how can one make an estimate of a var. So, for any alpha belonging to 0 1, all right. So, any alpha lying between 0 and 1. So, once you have fixed your alpha at a particular level, then an explicit formulation for a var alpha of x can be obtained in the form as minus 1 over alpha into expected value of x into the indicator function that x is less than q alpha of x. Remember that q alpha of x is a fixed quantity, plus this fixed quantity q alpha of x into alpha minus probability of x being strictly less than q alpha of x. So, this is the first explicit formula that we have in order to estimate our a bar of alpha. So, let us start the proof of this, and it goes as the following. So, I take x and I denote x minus, or I use x minus to denote the negative part of x. So, that is to be more specific, x minus is going to be minus minimum of x 0. Now, since this function f of x equal to minus of minus x minus is a non-decreasing function, right. So, that means is the negative of this quantity, that means minimum of x comma 0 is a non-decreasing function. Therefore, we can make use of the following result, that for any random variable y and beta belonging to 0 1, q beta of minus y minus. So, basically I am replacing x with this y. What is this going to be? This is going to be nothing but, from this definition I can write this as q beta of f of y. Now, since f is a non-decreasing function, so we can swap this f and q beta. So, this becomes f of q beta of y, and then I again make use of the definition of f x. So, this becomes minus of this argument. So, that is minus q beta of y minus. So, for convenience, let us write that this q alpha of x, remember this is a fixed quantity. So, the q alpha of x is equal to q alpha. So, just for the ease of notation. Okay, so now that I have this result set up, now what I can do is that I can start off with getting the result that I have stated here in order to have an expression for a bar of alpha. So, therefore, a bar of alpha of x, what is this going to be? This is going to be minus 1 over alpha. By definition, this minus 1 over alpha multiplied by integral from 0 to alpha q beta of x d beta. Now, this can be rewritten in the following form, that this can be rewritten as minus 1 over alpha integral 0 to alpha, within bracket I can write q beta of x minus q alpha into d beta minus q alpha. So, observe carefully that this particular term here, this integrand, the alphas will cancel out, and this integral of minus q alpha d beta with minus 1 over alpha outside, this exactly matches this value of q alpha. Okay, now I can now rewrite this in a slightly different form. So, this is going to be minus 1 over alpha integral 0 to alpha, and let me just focus on this term. And so, this is going to be written as minus q beta of x minus q alpha minus into d beta, and this q alpha remains as it is. Now, why was I able to switch from this term to this term? And the reason is that because your beta is less than or equal to alpha. So, if that is the case, when beta is less than or equal to alpha, then obviously your q beta of x is less than or equal to q alpha of x, which is q alpha. So, this means that by definition this quantity here, because the condition that q beta of x less than or equal to q alpha holds, this expression that I have here reduces to q beta of x into q alpha here. So, this can now be written as minus 1 over alpha integral 0 to 1 minus of q beta of x minus q alpha minus d beta minus q alpha. And this is going to be nothing but minus 1 over alpha integral 0 to 1 into. So, I can now basically make use of this property that I have here in order to obtain that this is going to be q beta into minus of x minus q alpha minus into d beta minus q alpha. And what is this going to be? This is going to be nothing but minus 1 over alpha into expected value of minus of x minus q alpha minus q alpha. And remember, this can now be put as minus 1 over alpha of integral x less than q alpha of x minus q alpha into dp minus q alpha. So, just a slight correction here, this should be actually q beta. So, this can now be rewritten as minus 1 over alpha into integral. So, I can split this up. So, this becomes integral x of dp, where x less than q alpha, and then you have integral q alpha dp into x less than q alpha, and I will have plus alpha q alpha. And this can now be written as minus 1 over alpha, and this is what? This is nothing but the definition of the expectation of x under this condition of x less than q alpha. So, this is going to be the expectation of the random variable x into the indicator function of x less than q alpha, and here I will essentially take this q alpha term in common because this is a fixed quantity, and from here I will get alpha minus integral of dp under this condition. So, this integral of dp under this condition is nothing but probability of this condition. So, probability of this event, that is probability of x strictly less than q alpha, and hence we have got the result. Okay, so, now that we have done this particular lemma or this proposition, and remember that this is in a generic case. So, let us now try to see the fallout of this in the discrete case, and we will state this as a corollary. So, now assume that x is a discrete random variable with probability that x equal to xi equal to pi, and such that p1 plus p2 all the way to pn is equal to 1. So, that means there are this random variable x takes x1 through xn values with the corresponding probabilities being p1 through pn, and these are ordered random variables, that is x1 strictly less than x2 all the way to strictly less than xn. Then a var alpha of x can be obtained as minus 1 over alpha into summation pi xi I is equal to 1 to k subscript alpha minus 1 plus, so I just need to add here a plus sign. So, plus x subscript k alpha into alpha minus summation pi I is equal to 1 to k alpha minus 1, where k alpha, as already we have seen in case of var, is the largest number such that summation pi I is equal to 1 to k alpha minus 1, this is less than or equal to alpha. So, let us just go through a proof of this, and the proof of this is the following. The proof of this is that we start off by recalling that q alpha of x is nothing but the negative of var alpha of x, and you remember that this is nothing but xk. So, hence probability that x less than q alpha of x is going to be summation pi I is equal to 1 to k alpha minus 1. So, therefore, what is going to be the expectation? So, I am going to make use of this definition in the discrete case or this result in the discrete case. So, the first term is this expectation, and then we will deal with this particular term. So, here the expected value of the random variable of 1 into the indicator function, this is going to be summation p I x I is equal to 1 to k alpha minus 1. So, therefore, we can now make use of the proposition to get that a bar alpha of x is minus 1 over alpha into this expected value of x into 1, or the indicator function that x is strictly less than q alpha of x, plus q alpha of x into alpha minus probability x is strictly less than q alpha of x. Now, this, as you have already seen from the previous step, this is nothing but, so I will just use this here. So, this is going to be summation p I x I is equal to 1 to k alpha minus 1. And what is q alpha of x? Q alpha of x from here is going to be x k alpha. This alpha remains as it is, and probability that x less than q alpha of x corresponds to your x going from 1 to x k alpha. So, this is going to be, now since there is a strict inequality, that means the event x less than q alpha of x is going to be those values of x which go all the way to the value of x preceding x k alpha, namely x k alpha minus 1. So, this is going to be simply summation p I is equal to 1 to k alpha minus 1. So, next I will just state a few results without proof. So, the first result that I state is the following, that if x is a random variable whose distribution function capital F subscript x is strictly increasing and continuous, then a bar alpha of x has a simpler form, that is, this is going to be equal to minus the expected value of x is less than or equal to q alpha of x. So, this gives you another way of writing or obtaining a bar alpha of x. So, this is the first result. And the second result is I want to give a simpler form. For that we will just need a lemma, so let me call it lemma 0, that for alpha belonging to 0 1, let q alpha be used to denote q alpha of x as before, and we define or set a new indicator function that is with 1 subscript s superscript alpha. This is defined as 1 indicator function for x strictly less than x alpha if probability of x equal to q alpha is 0 and 1 of x less than q alpha plus some kappa into 1 x equal to q alpha if probability of this event, that is probability of x equal to q alpha, is strictly greater than 0, where I have not defined kappa up till now, and kappa is nothing but alpha minus probability x strictly less than q alpha over probability of x equal to q alpha. So, under this circumstance, then the expected value of 1 x alpha, that is this value defined here, is equal to alpha for all omega belonging to omega, and this 1 x alpha of omega, this will belong to 0 1. And so, this brings me to another result, is that for any alpha belonging to 0 1, we have a bar alpha of x is going to be minus 1 over alpha e of x into this indicator function given here. So, essentially what we have? We now have, this is one form of a bar alpha. under a specific circumstance, this is another form of A bar alpha, and finally after having defined this kind of indicator function, we have obtained a third form of A bar alpha, but I am just stating this without proof. So, we next come to a definition which is going to lead us to the A bar in the context of the Black-Scholes framework. So, we define the upper tail conditional expectation, which will abbreviate as TCE of x as TCE alpha of x is minus expected value of x given that x is less than or equal to q alpha of x, and this is nothing but minus expected value of x given that x is less than or equal to minus var alpha of x, because by definition minus var alpha of x equal to q alpha of x. And when f x is continuous, then we have alpha is equal to probability that x less than or equal to q alpha of x, which is equal to probability that x is strictly less than q alpha of x. So, hence we can conclude that for continuous f x we have TCE alpha of x is equal to A bar alpha of x. Okay. So, this means that what it gives you is that you have defined what is TCE of alpha of x, and under the circumstance that the distribution function of x is continuous, this TCE alpha of x will give you the A bar of x. So, that means under this special circumstance you can have another way of finding out what is A bar alpha of x, and that is going to be given by TCE alpha of x. So, now this brings us to the last stage of our discussion on A bar, and it says the following, that recall that, so you recall that ST, that means if you start off with a stock price S0, then S0 into e raised to mu minus half sigma square capital T plus sigma square root of capital T into Z, this is going to be the value of the stock at time t using the geometric Brownian motion, where of course you have S0 is obviously is going to be greater than 0, your mu is belong to R, sigma greater than 0, and of course you have S0, mu and sigma, and only thing left is Z, and you recall that Z follows a standard normal distribution. So, then we have one last result pertaining to this, and it states the following, that for any q belonging to R, E of ST Z less, given the Z is less than or equal to Q, what is this going to be? So, let us look at this condition, what does it evaluate it to be? So, what is this going to be? This is going to be nothing but 1 over n q. By definition of conditional expectation, it is going to be 1 over probability of this is n over n of q, because Z follows the standard normal distribution and n of q is the cumulative normal distribution, into expected value of ST. So, this is going to be S0 into e raised to mu t into n of q minus sigma square root of t. So, here your n of q is going to be the cumulative distribution, that is minus infinity to q of the standard normal distribution, that is 1 over square root of 2 pi into e raised to minus x square over 2 into dx. Now, how do you go about the proof of this? So, the proof goes as follows. So, since probability of Z less than or equal to q is going to be equal to n of q, remember that Z follows n01 distribution, which is obviously going to be greater than 0. So, then we can make an evaluation of this. So, therefore, E of expected value of S of t into Z less than or equal to q, what is this going to be? This is going to be 1 over probability of Z less than or equal to q. So, that was the reason why I had to state this upfront. into integral from minus infinity to q. Remember that this is the condition that z must be less than or equal to q, into s of t, which is s0 into e raised to mu minus half sigma square t plus sigma square root of t into x, and here it is with respect to the distribution of z, which is 1 over square root of 2 pi into e raised to minus x square over 2 into dx. So, this is n of q. So, the denominator I will have of n of q, and the s naught and e raised to mu minus half sigma square t term, this is constant. So, this is going to be s naught into e raised to mu minus half sigma square into capital T, and I will have the integral from minus t infinity to q, and the remaining term that I will have is going to be the exponent of this and this term. So, this is simply going to be e raised to sigma square root of t x into 1 over square root of 2 pi into e raised to minus x square over 2 dx. So, after some rearrangement, this turns out to be, so I will have 1 over n q into s 0 into e raised to mu minus half sigma square capital T. So, I will multiply this with e raised to half sigma square t, and inside I will then have these two terms combined along with this term. It is going to give me 1 over square root of 2 pi into e raised to minus x minus sigma square root of t here whole square over 2 into dx. Okay. So, now this minus half sigma square t and plus half sigma square t will cancel out. So, I will get 1 over n q into s 0 into e raised to mu t, and I could define my x minus sigma square root of t to be equal to y. Then this integrand ends up being from minus infinity to q minus sigma square root of t into 1 over square root of 2 pi e raised to minus y square over 2 into some dy. And now what is this? This is nothing but the probability density function of the standard normal random variate, and this integral is the cumulative distribution from minus infinity to q minus sigma square root of t. So, this gives us, so I will get 1 over n q s 0 e raised to mu t, and this term here within my box, this becomes n into q minus sigma square root of t. So, hence you end up getting this result. So, you end up getting this result. Okay. So, now what I want to do is I just want to look at, so remember that our original motivation was to look at x, and what was x? X was nothing but the discounted gain, that is e raised to minus r t into s of t minus s 0. So, now I can make use of this result in order to make a final statement that for the discounted gain, and what is the discounted gain? This is x is equal to e raised to minus r t into s t minus s 0. What is going to be the a bar? Remember, at the end of the day, you are really interested in looking at what is the a bar of your discounted gain, and this is going to be nothing but s 0 minus 1 over alpha s 0 e raised to mu minus r into capital T n of q alpha of z minus sigma square root of t. So, how do you go about getting this result? The way you go about is the following. So, this is the proof of the result. Now, remember that, so recall that q alpha of s t is going to be equal to s 0 into e raised to mu minus half sigma square into capital T plus sigma square root of t into q alpha of z. So, therefore, what is x less than or equal to q alpha of x? This, now x less than or equal to q alpha of x, I can rewrite this x to be e raised to minus r t into s of t minus s 0. And what is q alpha of x? Q alpha of x nothing but q alpha of e raised to minus r t into s t minus S0. And now you observe carefully that this actually reduces. So, this relation then reduces to the condition that S of t less than or equal to q alpha of S of t. Now, if we replace the value of q alpha of S of t here and you replace the value of S of t, then this reduces to a much simpler form, that z is less than or equal to q alpha of z. Alright, now why did I abruptly start talking about x being less than or equal to q alpha of x? And the reason is that, remember that since x is a continuous distribution, remember that x is the discounted gain. So, this is a continuous distribution. So, that means that I can take advantage of the fact that if x is a continuous distribution, then the a bar alpha of x is going to be nothing but TCE alpha of x. And the TCE alpha of x involves the definition involves this value. So, in order to take advantage of the fact that these two are TCE alpha and a bar alpha are identical if x is a continuous distribution, I have a priori obtained this relation. So, TCE alpha of x is nothing but minus the expected value of all those x such that x is less than or equal to q alpha of x. Now, what is this? This is nothing but, so what is x? X is nothing but e raised to minus RT into ST minus S0 given, and remember this is something that I have by definition, and x less than or equal to q alpha of x in the preceding step, that is nothing but z is less than or equal to q alpha of z. And what is this going to be? S0 is a constant. So, this is not contingent on this condition. So, S0 will come out and minus e raised to this minus e raised to minus RT will come out. So, all you get is the expected value of S of t given that z is less than or equal to q alpha of z. Alright. And S of t of given z less than or equal to q alpha. So, this turns out to be S0 minus 1 over alpha into S0 into e raised to mu minus r of t into n of this q alpha of z minus sigma square root of t. So, remember that your q alpha is going to be now replaced with q alpha of z. So, I will conclude this topic by revisiting what is coherence. Remember that when I talked about coherence, I just focused on a bar alpha and motivated by what is going to be the defects or shortcomings of var alpha. So, in order to define coherence, we need to talk about what is a risk measure. So, by a risk measure, we mean a number rho x, which is real number, that is assigned to a random variable x to represent its risk. So, the following axioms are required for a satisfactory risk measure. So, this brings us to the definition. So, the definition is as follows, that a risk measure rho is said to be coherent if it satisfies the following properties. First of all, if it is monotone, and by monotone I mean that if x less than or equal to y, this implies that rho x is greater than or equal to rho y. Secondly, it is Cache invariant, that means rho of x plus m is going to be rho of x minus m. Thirdly, it is positively homogeneous, and this means that for all lambda greater than or equal to 0, rho of lambda x is equal to lambda of rho x. And fourthly, it is subadditive, that is, for any x y, rho of x plus y is less than or equal to rho x plus rho y. So, note that rho of x plus rho of x is going to be 0. So, here rho of x is a constant quantity. So, that means that rho of x plus, so this can be easily observed by the fact that of this property, that is rho of x plus rho of x, this is going to be nothing but rho x minus rho x, which is equal to 0. Now, the question is, why have I suddenly made an observation making use of the properties or the axioms that I have stated, and the reason is that you see rho of x is that quantity which renders rho of x plus rho x to be equal to 0. So, that means that rho of x is the minimum amount of additional investment we need to add to x to ensure that the final position eliminates risk as measured by rho. So, just to explain it in more detail, see, you have x and the risk measure is rho of x, which is probably greater than 0. Now, to this amount of x, if you add rho of x, which is like your m, what does this make? This means that your new position, that is x plus rho of x, this becomes rho of x plus rho of x, which I have said is equal to 0. So, earlier you possibly had a positive risk, but the additional amount of this cash m, this makes the overall risk to be equal to 0. So, that means that it is the least amount of additional investment we need to ensure that your risk is eliminated, that is, it is being rendered to be equal to 0. So, that means that if you add an amount of rho x, that this obviously is the resulting risk as given by rho of this position is going to be equal to 0, and if you add more than this rho of x, then obviously this quantity is going to end up being negative. So, suppose that you add an amount of twice rho x. So, rho of x plus twice rho x, what is this going to be? This is going to be rho of x minus twice rho of x. This is going to be minus rho of x, which is going to be less than 0. So, this entire narrative can then be summarized, in particular this statement can then be summarized as that rho of x is nothing but it is the smallest m, right, which will make sure that this becomes less than or equal to 0. So, that means the smallest real number m such that rho of x plus m is less than or equal to 0. And in the parlance of risk management, a position x is said to be acceptable as long as the risk is not positive. So, it is said to be acceptable if rho of x is less than or equal to 0. So, if you observe carefully here, if you go back to the definition that we have here, look at the properties, that if you observe that all these properties, these are satisfied by a var, but the subadditivity property is not satisfied by var, and that is the reason why var is not a coherent measure of risk, but a var is. So, this brings us to the end of this topic on risk management, and just to give a recap, what we have done is that we started by looking at what is the definition of upper and lower quantiles in the first lecture, and then we looked at what is var and looked at some of the properties of var, and in particular look at how are you going to calculate the var of a stock in the context of the geometric Brownian motion model. And in today's class we introduced the definition of the average value at risk, or AVAR, by noting the fact that VAR is not does not capture what is going to happen in terms of the losses that are that have a probability of less than the predefined alpha for which the VAR is being defined, and accordingly we defined a VAR which was nothing but like the expected loss, and we looked at several variants of how one can determine a VAR, culminating into a form for determining a VAR. First in case of the discrete time setup, and also finally we looked at using the geometric Brownian motion in case of calculating the AVAR for discounted gain of a risky asset. And we concluded by today's lecture by looking at a general definition or the axioms of coherent measure of risk, the most prominent example of which is the AVAR. Thank you for watching.